Well, hello and welcome again to our journey into linear algebra, and we've been calculating exponentials of matrices, and we've now seen how to find the exponential e to the a or e to the at of any square matrix, whether it's diagonalizable or not. You will have seen, especially in the case, say, of the 3 by 3 example, that the computations in finding this e to the at can be very involved, take a lot of steps and a lot of calculation, and we're going to see in the next section, when we look at systems of differential equations, that we're really only interested in not so much e to the at itself, but what it does when I multiply it by some particular vector. Now, in the case of an eigenvector, we have the following remarkably beautiful and very simple result. It tells us what this matrix e to the at does when you multiply it by an eigenvector, without ever looking at e to the at, which might be some horrible big matrix. So when you multiply it by e to the at times an eigenvector, look at what you get. You just get e to the lambda t, where lambda is the corresponding eigenvalue, times t, times the eigenvector you started with. That is beautifully simple. And it's worth seeing a proof of this. The proof is fairly straightforward and quite instructive, so it's worth actually going through a proof of this. So it incorporates lots of important ideas as well that we'll use elsewhere. So here's our proof. We take v in the eigenspace for lambda. So v is an eigenvector corresponding to eigenvalue lambda, and that of course means that a minus lambda iv is 0, because v is in the kernel of this matrix. That's where we get the eigenvector from in the first place. So when I work out e to the at times v, I'm going to replace the a with a minus lambda I, and then I better patch it up by multiplying by e to the lambda it. We've done this before, and this of course only works because the identity commutes with the matrix a minus lambda I. Otherwise, if I just had general matrices A and B here, this is not true, but I commutes with this, and so we can split this up. And as I mentioned before, e to the lambda it is just e to the lambda t times the identity matrix. And the identity matrix multiplied by this matrix just gives you that matrix back again. So just note what I've done from here to here. I get e to the lambda t times this matrix times vector v, and I'm going to expand this out as its series, which is the definition of how we calculate these things. So I'm going to expand this out as I plus a minus lambda it plus and so on in terms of its Taylor series, and I'm going to multiply this by the vector v. Now I times v just gives you back v again, and a minus lambda I times v gives you the 0 vector because of what we set up here. And similarly, when I multiply this matrix by v, I get 0. So when you multiply all of this infinite series times v, you don't get anything. It all is just the 0 vector. And so all that survives is e to the lambda t times v. That is a beautiful result, and the proof is so elegant and simple. I wanted to do an example. Let's have a look at a quick example. By the way, the result, if you've got your vector v, which is perhaps some linear combination of eigenvectors, not necessarily from the same eigenvalue, by the way, you can also do a similar sort of thing. So if you've got your v, which might be 3 times one eigenvector plus 5 times another, then you can simply use this result also in calculating that. Just as a very simple example, here is a matrix 3, 4, 5 minus 5. We want to work out e to the at times 2, 1 without ever calculating this beast here. So here's the solution of this. It's very short and sweet. And so here's our matrix. I've already calculated that the eigenvalues of this matrix are 5 and minus 7. You can check at least the traces match. So the trace of this one's minus 2 and the sum of these is minus 2. I just worked out the eigenspace for 5, and I came up, and of course that means you subtract 5 off the main diagonal, you'll get minus 2, 4 here, and so the kernel of that will be the span of 2, 1. So there's my eigenvector. Now applying our theorem, e to the at times 2, 1 is just e to the lambda t times the vector 2, 1, and that's it. It's very, very simple. Beautiful result. Now we'd like to be able to extend this to the case where v is a generalised eigenvector. So if v is a generalised eigenvector, or a linear combination of generalised eigenvectors, we can also find e to the at times v, and we can do it fairly easily, certainly much more easily than having to calculate this monster of a matrix in here, the e to the at. So here's our little theorem, and it says we take A to be an n by n matrix, lambda is an eigenvalue of A, and we take V1 to be any vector in any of the generalised eigenspaces. It doesn't have to be the last one, it can be in any of the generalised eigenspaces, my vector V1, and you construct, as we've done before, this chain. So you take your V1, you multiply it by A minus lambda I, you get a V2, multiply it by A minus lambda I again, you get a vector V3, and you keep going, and of course eventually from the onion diagram you'll end up in the eigenspace, and once you're in the eigenspace, when you multiply by A minus lambda I again, you're just going to get the 0 vector. So given that you've constructed this chain, then here's the punchline. E to the at times this vector v1, this is any generalised eigenvector, is e to the lambda t times the v1 you started with, plus t times the next vector in the chain, tv2, plus 1 on 2 factorial t squared times the next vector in the chain, and all the way down till you get to 1 on k minus 1 factorial, t to the k minus 1 v sub k, the last non-zero vector, i.e. the eigenvector in the chain. And the proof again is worth looking at. It's quite simple and quite lovely result. So e to the at, we do the same trick again. Instead of a, we want a minus lambda I, and so we split this up. We can only do this again because I commutes with a minus lambda I, and again this matrix here is just I times e to the lambda t, and the I multiplied by this just gives you e to the t a minus lambda I. Now we're going to expand this thing out in series now. So e to the t a minus lambda I, there's its Maclaurin series as before. And now we're going to multiply this, of course, by this vector v1. So when we multiply a minus lambda I times v1, well, of course, by the way we constructed our chain up here, I'm just going to get vector v2. And if I do it twice, if I multiply this matrix times v1, well, then I multiply it by a minus lambda I once, gives me v2, and do it again, you get v3. So this is going to be v3, and you keep going all the way down until you get to 0. And then taking this matrix up here and multiplying this series by v1 gives me v1 plus tv2 plus 1 on 2 factorial t squared v3, and so on all the way down to vk. And finally then we multiply everything through by e to the lambda t, and we get the formula that we had up here. Well, again, best to see this by example. So we'll have a look at an example here. We're going to take the matrix A, which is 10, 1, minus 9, 4. I'm going to multiply this matrix by 1, minus 3, and by 1, 2, without ever calculating what this matrix is. So here's an example of that. So here's our matrix. Now in this case I tell you that 7 is the only eigenvalue, and you can check from the trace, 10 and 4 is 14, 2 7s are 14, so that makes sense. And if I take the eigenspace for 7, so I subtract 7 off the main diagonal, I get 3, 1. So the eigenspace then is spanned by the vector 1 minus 3. Now I like to draw the onion. I like the onion, it's lovely. Unlike most onions, this one does not bring tears to the eyes. This is a lovely little diagram. So this is my eigenvector in here. And if we take the kernel of a minus 7i squared, we're going to pick up another generalised eigenvector. And of course, by this stage, we've got all of R2 because we've now got two linearly independent vectors in 2 dimensions. So we get all of R2. Now what that means is then that the vector 1, 2 that we're about to play with, this one must be a generalised eigenvector because every vector in R2 is either a multiple of this one, or that is in this space, or it's got to be in this space. And so this is a generalised eigenvector for A. Now we're asked to calculate e to the at times 1, 3. Well, 1, 3 was our eigenvector. So this is easy. This is just e to the 7t times 1 minus 3. Now for 1, 2, we need to compute a chain. So I've computed the chain down here. So I take 1, 2, I multiply it by a minus 7i. I'll leave you to check that you get 5 minus 15. Now of course this has to be in the eigenspace. So this must be a multiple of my eigenvector, and of course it is. It's just 5 times the eigenvector. If you were to do this again, I'll leave you to check, you must of course get the 0 vector. So plugging that back in, so e to the at times 1, 2 by our theorem says this is e to the 7t times 1, 2 plus t times the next chain vector, which was 5 minus 15, and there it is. So we've calculated what e to the at does to the vector 1, 2 without ever calculating the vector e to the at. Now finally, I wanted to do an example here of a couple of examples to show you that in the case where A has only one eigenvalue, then it's really easy to find e to the at. This only works when there's only one eigenvalue. In general, this doesn't work otherwise, but if you've got only one eigenvalue, then e to the at is, you can calculate this with a fair degree of ease without having to do all of the Jordan blocks and forms and things. So I'm going to do a 2 by 2 one of these, and then a 3 by 3 one. So here is our matrix A, which is this one here, 5 minus 3, 12 minus 7. It's got a sole eigenvalue of minus 1. You can check that again because the trace of this is minus 2. Minus 1 minus 1 is minus 2. So that means then that A plus I, all squared, is the 0 matrix. So again, in terms of the onion, if you work out the eigenspace of this, there's only one eigenvector. You need to go to the generalised eigenspace to pick up the generalised eigenvector. And so the kernel of this is 2-dimensional. That means the nullity is 2, the rank is 0, so this matrix is the 0 matrix. And again, we're just going to use this trick again. I'm just going to replace A with A plus I, and then I have to put an e to the minus t here. I've left out one of the extra step of putting an I and simplifying here. We've seen this before. So this is e to the minus t. Expand this in series, the usual way. And of course, this matrix here is 0 matrix, and all of the matrices from here on are all going to be 0. So I'm just going to get e to the minus t times I plus I t. So there's the identity. There's A plus I. You add 1 to the main diagonal, you get this, times t. And finally, I just put them all together in one matrix. And so there is e to the at without having to calculate the Jordan forms or P matrices and so on, and chains. I'm going to do one more example just to finish off with, which is a 3 by 3, just to show you that how useful this idea is. It only works if you've got one eigenvalue. So again here, if I tell you it's one eigenvalue, it's got to be 3. The trace of this is 9. So I worked out the eigenspace, which turned out to be one-dimensional. So when I subtract 3 from the main diagonal, I get this matrix, and this one clearly has rank 2, nullity 1. So there's only one eigenvector hiding in the kernel here. So the onion looks like this. We've got one eigenvector. We need to go to the next kernel out to get the next eigenvector, and the next kernel out to get the next one. Now, so that means by the time I get to the third kernel, I've now got a kernel of a matrix which is now 3-dimensional, so the rank is 0. So the matrix must be a 0 matrix when we get to the a minus 3i cubed. I do have to calculate, one calculation I do have to do by hand, which I did here, was to work out a minus 3i squared. So I had to do that by hand. And that was the only calculation really I had to do here. Now again, e to the at, you replace a with a minus 3i, and then you patch it up, and that's e to the 3t, and you expand this out in series. So you get a minus 3it, a minus 3i squared, t squared on 2 factorial, plus everything else will be 0 matrices here. And finally plug all this in. So I get e to the 3t, there's the identity, there's a minus 3i that we had before, there's a minus 3i squared, which I had to calculate by hand, times t squared on 2 factorial. And finally I put all those together into this one horrible big matrix. I've just added all the entries together, and there's the e to the at. And you can see how horrible it looks. We would not want to have to do this by using Jordan forms and chains and blocks and things. This is P matrices. This is a much easier method, but of course it only works if you've only got one eigenvalue. Well, in the next series of videos, we're going to have a look at applying all of this to solving systems of differential equations.